The lecture today is about language representation and also some focus on RNNs. I want to talk and take the time to understand word representation, sentence level representation, and also other very interesting aspects of sentences and language, such as syntax and the language structure. We took the time last Tuesday to look at visual representation and understand what makes these representations powerful, but also their limitations. And I will try to do a similar thing for language in this lecture. So word representation, how do you represent? And linguists and now computational linguists have or had for a long time this goal, and specifically the computational linguists and the natural language processing researchers, to find a way to take these words within a sentence and find a way to represent its meaning. What is the meaning of a word? And the goal would be that we have, in the case of computational representation, have these vectors or these numerical representation that are an approximation of the meaning of the word. That has been a goal for many years, and we've seen great progress in the, I will say the last 7 to 8 years in using neural representation for that. And to make you think and understand what is beyond these current technologies, it's really interesting to try to find and do the exercise a little bit for what, like, think a little bit almost like a computer for a second. So what is the meaning of Bardawak? Bardawak. Nobody knows? Okay, let's look at text corpus and let's look at where this word is used. So he handed her a glass, sorry for the typo, her a glass of Bardawak. Okay, that's probably Bardawak, something we can drink. Beef dishes are made to complement Bardawak. Okay, now you start learning what Bardawak is. Nigel staggered to his feet, face flushed from too much Bardawak. You probably start having Malbec, one of the lesser known Bardawak grapes, or spawn. I dine of bread and cheese and this excellent Bardawak. The drinks were delicious, blood red Bardawak as well as sweet Rhenish. So by now, you probably have an idea of what Bardawak is about, because you've seen it in different contexts. Without knowing what the word itself is, its context, and by context meaning the words that are happening around this, gives you an idea of what the meaning of the word itself. And that is the key idea behind a lot of the current representation, is that the context behind around the word is really informative in approximating its meaning. Because just from this, you can find that Bardawak is a heavy red alcoholic beverage made from grapes. You can pick up from all the context without knowing exactly what Bardawak is. And Bardawak is not a type of wine that I'm aware of, but you can guess it's probably something like a wine. So how do this idea came? This idea has been there for a while. This idea way before Word2Vec and all this, there's this idea of distributional hypothesis that you can approximate the meaning by its surrounding words. And that has been done previously with some analytical approaches that I'm going to give a hint at, and before I talk about the neural approach that is the most common one. But the idea is words used in similar contexts probably lie close together. He was walking away because he was running away because, I mean, even if I hide this box, you will know, I mean, everything happening in this box probably has a similar action or similar meaning. And that's the idea that if two words have the same kind of context, they must be close to each other. So without even like really knowing the context, knowing the meaning itself, the idea of distributional hypothesis allows you to, words that have the same meaning will be close together, and words that have different meanings should be further apart. That's the idea here. They should be in a different part of the space. And that's the idea of the distributional hypothesis, learning a computational representation. And so instead of capturing co-occurrence counts directly, we predict the surround leg. So it's not that you're counting the number of words, you're going to in fact count the number of words around it. You will kind of hide the box where the word happened and look at all the words that happen before or after this. And in this case, the J is anything before and after the current words. And so the idea here, the way you can look at it, and that's the way distributional hypotheses were often studied back in the days, is like, I want to know numerically how to represent the word dog, and how to represent all of these words like knife, cat, dog, boat, cup, pig, and banana. So one way to do would be to look at all the other words around, like when is it that you use the word knife? What are the other words happening in this? And maybe just for the purpose of here, I'm just going to learn and look at the verbs happening around that word knife. And so you get a knife, you use a knife, you rarely kill a knife, although you can hear, very hard to hear a knife, although you can still hear it, but rarely or less often. The dog you can get, you can hear, you can see. And so you can see that these words happen with different distribution. And so the distribution of how often they co-occur can be put in a matrix. And this matrix will give us the information of a representation for this word. And so you can use this. And now what I will do, just for the purpose of here, and I will use two of these, use and get. I will use these use and get, and I will plot them in a 2D. So you have use and get. And now you can see where each of them are, like cat, dog, boat, and knife. And so you can see it gives you some proximity. Knife is further from both cat and dogs. So that's the first thing when you look at this. But the important thing here, and what will become very intuitive when we also, the reason we use multiplication often to compare two word representation, is that the Euclidean distance between two values, two of these positions, is not as informative as the direction of it. What it means, the fact that dog is here instead of here, 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 or here, the only reason it is at this position is that it happened more often in our corpus. It happened 118 times here and maybe 10 times here. What is important is more the ratio between them. That's the most response. The fact that it happened really often is not as much of a good descriptor of the meaning of a word, but the ratio between use and get is more useful. So the angle, and so like the distance itself just means that dog was used more often, the word in that corpus. What is the most important is in fact the angle of it. So the angle between the vector dog and the vector cat is meaningful. That one is meaningful. So the ratio of use and get, and right now I'm just putting it 2D. You can imagine these vectors could be multidimensional. So we're talking about the distance between the vectors. This will be the key to represent. And so that intuition will be important as you do word representation and similarity between word representation. A lot of the word2vec and all this, they have the same aspect that Euclidean distance, like just between two vectors, is not as meaningful as another way to do it, it will be to just normalize your vector, and then Euclidean distance will be similar, or use the angle as I mentioned. So this is one important thing. But then the question is how to learn these representation, these feature representation, and how to do it with a neural network. And so it turned out Word2Vec, although Word2Vec, which now I know these days we use extensions to that, but Word2Vec, when it came out about 2015 or around that time, if I remember correctly, maybe a little bit before that, the Word2Vec, the idea is similar to the distributional hypothesis, but I will use a one-layer neural network to do the trick here. What I do is, if you remember, how do I represent? I told you in the lecture 2.1, how do you represent words? The way Word2Vec and a lot of these others, the way the input for it is almost always a one-hot encoding. 100,000 here is just the full length of the dictionary. And my goal is to see how well can I predict the context, because I hypothesize that the context, the words around it are the most important, or are very important to explain the context, to explain the meaning of the words. And so what we will do is create another vector, which is the context. So for every word, I have its context explained also in a one-hot encoding. And the goal is to learn a neural network. The neural network, the neural network will take this very high dimensional one layer neural, and in fact, it could be as simple as a linear activation function, gives you some intermediate representation, which could be the size of 300, and then another neural network that then takes this, there's a transpose here, that will take this to finally give me the output that I'm trying to predict, which is the context. So then this neural networks, the feed forward says, for any word you give me, I will learn a small representation, and that small representation will be really good at predicting the context. And then at test time, what you will do is simply removing this. You remove this part, and then you keep, and so Word2Vec is only this part. It's a large matrix in the sense of 100,000 by 300. Now, these days, you can see extensions of that with taking context, taking sentence representation, and we'll discuss that. But the core of it, of representing words, is this idea of distributional hypothesis. So if we have a vocabulary of 100,000, and we were to do similarity with that 100,000 vector, that similarity would not be meaningful. But now if we run this 100,000 into our vector, we get this vector representation maybe of 300. Then these, if you look at similarity, this similarity is a lot more meaningful. And it's meaningful because the value it's predicting, the value it's predicting is in fact whatever was needed to predict the context. And since these two words had the same context, then they have the same meaning, or at least approximate meaning. One really cute thing that came out when the original Word2Vec paper came out is that, in fact, they went ahead and started at looking at the representations and looking at arithmetics of, like, can you do something like take the word king and get its representation, get the word man, take its representation, woman, and then you take the representation for king minus man plus woman, and then get a new representation, and then just sample from that. And then the closest one was very, very close to queen. And so these algebraic, and they tried for like looking at, is there like some relationship also, such as a country and their between the country and the capitals from there. So that was really interesting to see these relationship. There are issues with this, although there are some of these that are really intuitive and that looks really well. Unfortunately, there are words that from a human perspective will look very different, like positive, negative, hot and cold, like things that looks very different but happen to be used very often with the same context. And because they've been used in the same context, their representation will end up very similar. And so that's one of the issues with this. And there's been some follow-up work trying to address some of it, but it's still something to be aware that many of the current word representation have. The second one is that the inputs are one-hot encoding, and so they created the dictionary, and the dictionary is based on like the morphology, like the representation of the word by character. So if two words like plant like a tree or like a plant, or the plant like a factory, they have the same spelling. And unfortunately, this approach will not differentiate the two. Both of them will have the same one-hot encoding, but there will be two different contexts where the same one-hot encoding will be used. And so these will have kind of almost the average of both. So then the issue is you would like to be able to differentiate that. So these are some of the issue. The second one that I talk about, plant and plant, one of the way you could solve it is by look at the words that are around it, because plant, the phrases that are used where the word plant is mostly about like a flower or organic then element, and then in that case you probably have very different other words happening at the same time. So when I encode the words, maybe I should not just encode one word at a time. I should look at the full sentence, and we'll discuss in a little bit how to do it. But if you encode one word at a time, which was for a while how we were doing it, we have some of these issues. There's been quite a few these representation. There was also an extension, fast text. There was interesting because it was looking almost as a character level representation as a way to speed up things. Since then, I will say these days, most people will still use, some people will use word level for some application, but many of the application will be sentence level. What it means, sentence level, is I take a full sentence and then I encode all my words. And so for every word, I will have an encoding. So that's one way of encoding my sentence. Another way to encode the sentence is take all my input words and in fact only get one vector for the whole sentence. So when you see the word sentence level representation, both of them could be done. But and a lot of these approaches will give you both of them. So we'll have more details about Elmo. It's for this lecture today, and Bert and Roberta and all this will talk about self-attention in 2 weeks, although you're really welcome to look at it in the meantime. I know that a lot of you love neural networks and eat it for breakfast, and so that's great, and we still use it a lot in our research, and that's what this course is about. But I want you to remember that there's other ways you could also represent words. And it's very healthy to think about it, because sometimes maybe you have a smaller data set, or you want your model to be more interpretable. And if you want a model that's interpretable, you also want a model that has interpretable features. And so for all of these reasons, you having not only just throwing all of your data into like a neural network, having input features that are interpretable can be very meaningful and help you understand what has been learned. So there has been one of them, and I would say one of the most popular, at least it was until recently, is LIWC. LIWC is language inquiry word count. What it is this very great work. It was started with Penny Baker. It was to study, I think some of it was even looking at depression and some mental health issues. but try to create dictionaries. I think there's a total of about 84 or 80 plus of these dictionaries. And there's a dictionary for each topic. And so they have like, I think 12 categories, and for each of them different topic. So the topic you could say is a feature or it's a dimension. So your vector you could imagine of LIWC be 84, and so one value. And this will be about how much a word, how often a word was seen in a positive context, how it's seen in a negative context, how often is seen in a past tense context, how often in the present. So this is a lookup table that has been done. The software is unfortunately commercial, but if you're interested to do that and use it for your research, please contact the TA. We may be able to help with that. So these approaches are called lexicon-based approaches. There's been quite a few over the years that have been created. Some of them are just for sentiment analysis, like each word, like knowing its sentiment. And so you can look at lookup. LIWC is a little bit more exhaustive in this. And then since then, many companies and some research group also created tools. These are not lookup based or lexicon based, but they're also useful. A lot of them will have like sentiment analysis tools, and some other attributes of language will be described there. So I will suggest to look at them as well. So because word representation are great, but sometimes if you have either you have the hypothesis you'd like to test, like you'd like to know, for example, if affiliation is something important in your corpus, then these will be useful. But so I want to give you that. But the core, and most of you, when you look at language in your project, probably will use neural representations to do your work. And so I will focus the rest of the lecture today on how to learn these neural representation, and also some intuition on the NLP side as well. So language is could be seen as a sequence of tokens. That's one way to think about it. Although speech is more complex because there's also the phonology and morphology aspect of language. So there's a lot more, and then there's a syntax, semantic, and pragmatics. But from a low-level raw representation, sentences you can be seen as a sequence of tokens. And so from a sequence modeling perspective or sentence modeling perspective, there are at least 4 or 5 different kind of tasks you can be doing. One is called sequence label prediction. Given all of my tokens, all of my words, being able to predict one unique labels. There is also the possibility of predicting one label for each word. Example of that is part of speech tagging, where you'd like to know the nouns, you'd like to know the verbs within a sentence, you'd like to know these different parts of the sentence. You could also do sentiment analysis, maybe every possible words or every phrases as well. So that's another, but this is often called sequence prediction. Another is, and probably what you will hopefully remember the most of these lectures and the moving forward, is like the idea of sequence representation. Sequence representation is the idea of not directly yet doing the labeling and classification task, which will come later, but the goal is to take this sentence or take some specific words in the sentence or some specific part in that sentence and be able to have a representation for it. And so we talked a second ago about word-to-vec. Word-to-vec is a sequence or a sentence. Word-to-vec is a word-level representation. And we'll talk in a little bit about how to make it at a sentence level. But we know yet to do the word representation. And if I ask you, like, without telling you how the other approaches are working, how do I do a sentence representation with word2vec? The simple way, averaging. You just average your word2vec. And I must say, we will study all a lot fancier approaches, but averaging word2vec or averaging word2vec with a little bit of an attention model on top of it can be very powerful. The sentence representation are performing better, but it's not always clear that in all tasks you need those a lot more complex representations. So, so just something to be aware. Word2vec has its own good. And I told you, always start with simple. Like we talked in the last week about nearest neighbors as always a baseline model. I think it's always healthy when you are doing something with language, just do word2vec just for test, just so that you know what your baseline is. I think it's healthy to try these simple approach. And one thing which is, I don't know, I'm sure at that point was well taught, the term, but now these days it can be confusing, is the term language model. But it is a confusing term because language model could be, if I just tell you language model and you never took a class in NLP, you will be confused. You will say, oh, it's a model that models something about language. But in the community, in NLP, natural language processing, and computational linguistics, language model means, and speech recognition, that's also very important in that community, is language model means something very specific. It's a predictive model. It's a predictive model of taking some words, predicting the next word. Language model is seen in that way. Or you could say another way to think about it is, given the sentence, what is the probability that this sentence is to be happening in a normal English corpus, either spoken or written? So language models, so predicting the next word, it can be seen. So that's the term language model. And so I apologize for that terminology, but we have to live with that one. A language model we're used, and we will use them quite a bit, and these predicting the next one. So given that I have these predicting the next one, we will use them, for example, in language generation. We'll talk about it with when we look quickly at machine translation. But if I give you a vector of maybe all of these, like word2vec, I do word2vec, 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 I get a vector from it, and then I say, what is the likely next word? And then from this next word that I predicted, I then slide my window and then again do word2vec to word2vec, word2vec, and then predict the next word. And then this way, I can start from only a few words and get the whole sentence generated that way. And that's what you could use the language generation model, like a language model like this. The trick is you can also learn it maybe not even with some initial words, but just from an initial vector. And that's what we'll look at example. The other thing is that language model here can be used also for image captioning. So I take an image, run it through a CNN, and then take this value and find a way, learn a prediction language model that predict the next words. And so I take this, there will be a translation, and then there will be a language model. So it has, in fact, 3 steps. I encode the image, I translate, and then I generate the language. Language models were the most popular back in the days for speech recognition. And the idea here is as I predict the word sequence, so the speech recognition is a translation problem. Speech recognition is a translation. You hear, you have these wave, take it to a spectrogram, if we do it in a computational way, or MEL frequencies, MFCC in your ears. And I want to predict and be able to detect, like find out what the words are. And one of the probabilistic approach that was very popular back in the days, was to think about it in a Bayesian way and look at it and see like look at the likelihood, but then look at your prior. And the prior here, this prior here is your language model, like how likely these words are to happen in English corpus, a normal English corpus. And that is the one way to use language model. So how do you train and learn these language models, these different sequence model or sentence models with neural network? And the challenges when you learn these sentence models is to be able to do it so that it handles variable lengths, because not every sentences, it would be wonderful if all sentences were always 20 words long. There may be some, you could probably create a language like this. That would be a challenging language to create. Anyway, but yeah, sentences are variable lengths. And so how do you handle this in your algorithm? Padding could be an option, but you would like to also look at approaches that allows different lengths in a more concise way. You want to always keep the number of parameters to a minimum. If you remember the CNN, what was the beauty of it is that it was tying the weights between all of these convolutions in your kernel and your convolution processing. It was tying the weights and making it very efficient and just learning the bare minimum. And that's something like this we would like, but for a sequence, we would like to do that. And we want to take advantage of redundancy, as I hinted when I talk about a number of parameters. And so one approach that was very popular up to 2 years ago, and it's still quite powerful. In fact, there's some great work that showed that RNN can be as powerful sometimes as some of the recent transformer with some tweak to it. So there's still something you should know about. And even though you will hear often that representation of language through transformer and self-attentions, which we will talk in 2 weeks, recurrent neural networks are very useful. And I want to put that notation. I find this notation of neural networks the best when it's time to talk about gradient propagation. So I want to look, so this look fancy, but what it is, it's a one-layer neural network. So your input, your one-layer neural network, and then you have maybe one hidden layer, I say, and here you have maybe your softmax or something. So these are your score, and then you have finally a specific loss that you define. The loss is comparing your scores with the ground truth labels. And if you remember, there will be some specific weights associated. There's some weights maybe associated with each of these different layers. And so this is a normal feed-forward neural network. And the beauty of the recurrent neural network, it's only adding one new set of weights, and that's the new set of weights here that I show with this notation. And what it is that when I have a sequence of input, suddenly I have the U that tells me how the input, the relationship, the feed-forward relationship where between the input and that layer H at time t. But then I will also have a relationship of time t and t minus 1. So ht will be both at time t, the evidence at time t, plus the evidence from the previous time step. And both of them will be weighted through that h. And it's easier to see it visually by unrolling this. So I'm just unrolling the same, the equations are exactly the same. I'm just unrolling it over time. And so I have in this, this representation suppose that you have one output for every time step. So maybe part of speech tagging. So every input has one output. There is some that also could have one output only for the whole sentence. And that's in that case, you will not have this part here. this part here will be. So this is a recurrent neural network, and I just want to remind you the key aspect, because you're unrolling, I unroll it, but you have to remember that I'm in fact tying the weights. So the V is the same. So the way I process the X and I produce my scores is going to use the same U and the same V and the same W, in fact, at every time step. So all of them are using the same V and the same U. So the equation here that I see here, I use it at time 1, I use it at time 2, time 3, time 4. So this is used at all them, and that's efficient. But it goes with the hypothesis. It's mostly telling you that every time step, the way I'm encoding my words is the same. I can use the same function at every time step. And that advantage is the same as CNN by reducing the number of parameters. So, and so that's something to, when you see an RNN the first time you think maybe there will be a different set of parameters for each of them. No, there's different, you may think that there's a different one for each of them, but it's the same one. It also allows me to unroll as long as I want, because now if I have a sentence and it's only a 3 length 3, I can just unroll 3 times. If I have a 20, I can unroll it 20 times, but the parameters are going to be the same in all of the case. And the back propagation is going to be the same. So you always start from 1, and then you go and have the local gradient, and then that will give you, for the first step, that's the same rule that is done. And then you go down and you go for the next one. And here's the beauty of it. That's the next one, where not only at that point, so these 2 steps are exactly like a typical neural network feed forward. The beauty of it is for any other of this unrolled one before, any of the one before, like sorry, I'm coming back, but for any of these before, for like, for either like H2, H3, when I compute it here, when I unroll for this one, then that's the big difference, is that the gradient is going to start, you always start from the end of your sequence. An RNN is a directional graph. So I start from the end. This is all the same as a typical gradient descent, but then the gradient is going to be propagated, yes, to this variable, but also it's going to be propagated to all of the other unrolled time samples. And at this time t-1, I will get my gradient from this, but I also grade it from the loss that was for the t-1. All of them will be added there. So that's the main intuition into that, and that's what allows you to compute efficiently, analytically, the gradient for the backpropagation. It's called backpropagation through time. So let's use it in a few examples, and I also have a few questions for you. So, I can now use this to predict like probability of the word being positive. Let's say I have each of these words and I want to do sentiment analysis at the word level. So I have this information and I want to be able to know at the word level, is it positive or not? And so I can use my RNN and the backpropagation. If you remember, I will have my scores and then I can predict with the ground truth. And then that will allow me to go and propagate my loss, my gradient. And then I will also propagate and then I go down. But I will also get some loss from here. And then I propagate down and I will also get loss from here. And now the question for you is, what is the loss function for this when I optimize? Because the problem is I kind of have many losses. I have a loss here, I have a loss here, I have a loss here. So what is the typical way that I handle all of these, all different losses? Yeah. Okay, you just sum them. Okay, that's just the idea here. You just can sum them over the whole sequence. So that was easy, or relatively easy. Now, what if it's a sequence, but I only have one label for the whole sequence? Then what you will do is you will ignore all these scores here. You will not even try to create like scores for ideal for anyone and all of these. You will in fact only have one prediction at the end, and then what is your loss? Loss is easier because the loss is just the loss of the last one. Okay, so the intuition here is that you can go from left, and we'll see later that there's some trick to make it bidirectional, but here you will suppose that the language goes from left to right. And so as you go, you will hope that evidences gets accumulated, and hopefully here you will be able to have in the prediction of the score. What's really nice, if you train your model this way, or even if you train it this way, what's really nice is once you train that model, what you get for free is also called sentence representation. It will be a sentence representation that is specific for the task of let's say, in this case, it was sentiment representation. But that, if I take this one here, if I take this value here, before I make my score predictions, this is a sequence representation. And so that's a nice way possibly to encode my sentence, would be to train it for a task. And that task in this case could be positive, or the task could be about predicting the next sentence. That's something we'll discuss, and that some people have done it. Because if you remember in Word2Vec, the way to predict and train the neural network was to train the neural network to predict from a word input, predict the context. So you could imagine learning a sentence representation that says, hey, let me try to predict the next sentence and the previous sentence. And that was let me be sure, the tot vector, or tot2vec, I forgot the exact name, was one paper from Toronto, University of Toronto. Or you can do any other task you can think of. We'll discuss some also in 2 weeks. But the sentence representation nicely is like you get your sentence encoded, and then suddenly you have a representation. And you can use this representation. Now, you remember there's another piece we talked earlier, which is about language model. Language model, what it does, it takes a representation, and then it can generate words by taking the representation and then generate the next word. They get the representation of that next word, and then predict the next word, and then going back and forth, not back and forth, going forward with your prediction. And so if you do this, you could use this, and that's called a sequence-to-sequence model.